Yes, sir.
ওরা যে মতো চেয়ারে হয়ে গেল, বয়স বাড়লো না, এত মহা মুশকিল তো।
I think we are live now. Sir, shuru kori.
Okay.
Okay, good morning, everyone. I'm an assistant professor in the Department of Chemistry at Ramkrishna Mission Vidya Mandir, Belur. On behalf of our department, I welcome every one of you in our virtual studio and who are watching online on YouTube to the day-long seminar. I must thank you for the overwhelming response that we received in such a short notice. This is truly amazing. We have two sessions today. One starts right after the inaugural speech and the second one after the lunch. In my opinion, this is a major drawback in our webinars that the organizers are unable to provide lunch on an online platform. Now, it would have been much nicer to host you in our beautiful campus right beside the River Ganga and the Belur Math. As the seminar title describes, we tried our best to diversify the areas of research on chemical science. The three speakers that are kind enough to agree to talk about their research in our webinar are from three eminent institutions, and they will talk about three different branches of chemistry. The majority of our audience is undergraduate students, and we hope it may help to shape their mind for scientific research in the coming days. That being said, I will request our principal Maharaj, Swami Ekochitanandaji, to give a formal welcome address. Over to you, Maharaj.
Om Sahana Bhavatu Sahano Bhunaktu Sahaviryam Karavavahai Tejasvinavadhitamastu ma vidvishavahai. Om Shanti Shanti Shanti. Hari Om. Respected Professor Anindya Datta, Professor Pinaki Chaudhary, Professor Niladri Patra, respected Professor Devashish, our departmental head, all other faculty members of the Department of Chemistry, and dear students. My respect, namaskar, good wishes, and now in due places. Finally, so we are nearing the end of this year-long stalemate, Corona stalemate, and we are happy that we are having such a academic Congress discussion session today. Our students have suffered a lot. There's no elaboration to say that. And definitely today's day-long seminar will definitely be a big boon to them. Now and then we have been trying to connect with them and feed them with their academic delicacies, but definitely due to this corona pandemic situation, it's not been an easy task to connect with them all. Definitely, I hope and pray that today's seminar will be much beneficial to them, all of our students. Another Bhagavad Gita describes that among all possible yajnas, all possible sacrifices, jnana yajna, the sacrifice done through performance of cultivation of knowledge is the best one, the superior one. Therefore, whatever maybe their capability, I don't know to what degree they can understand the discussion that will be following today, but undoubtedly they will be benefited. That's what I expect, and I do pray. Once again, on behalf of Vidya Mandira family and on behalf of the Department of Chemistry, I welcome Professor Datta, Professor Chaudhary, and Professor Niladri Patra. Definitely, today or tomorrow, this period will be over. Corona carnage, and one day we shall be having the privilege of inviting them to our campus. With this prayer, let me finish up. Om Shanti Shanti Shanti. Hari Om Tat Sat. Shri Ramakrishna Arpanamastu.
Thank you, Maharaj, for your wise words. Now, without much delay, I will request Professor Pinaki Chaudhary, who was also my teacher at the time of my BSc at this college, and currently a professor at the University of Calcutta in the Department of Chemistry. I will request Professor Chaudhary to introduce and welcome our first speaker, Professor Anindya Datta from IIT Bombay. Over to you, Professor Chaudhary.
for giving me this opportunity to introduce my very dear friend, Anindo. Professor Anindo Datta is somewhat not a very, close term. Anindo is better for me, as it has been for the last 31 years since basically we have been students from Presidency College, and then again at Cultivation of Science, where we did our PhD together. But the thing is that I have to give a formal introduction to Anindo because this is a formal platform. Basically, Anindo did his BSc from Presidency College, Kolkata in 1992 and his MSc from University of Calcutta in 1994. Then he went on to do his PhD with Professor Konkon Bhattacharya at Indian Association for the Cultivation of Science and completed his PhD in 1998. Then basically he went abroad for his postdoc and then came back and he joined IIT Bombay sometime probably in 2002-2003. Presently, he is serving as the head of the department since May 2018 and he is a full professor in the department. Anindo has received several recognitions for his work, for his research and for his teaching. Notably, he is the recipient of the Chemical Research Society of India Bronze Medal and also he is presently a fellow of the National Academy of Sciences. He is also the head of the Nanoscience Center at IIT Bombay. His area of research is broadly in the field of photophysics and photochemistry of chemical systems under various situations and various environments. And he has a number of impressive publications to his credit, more than 100 in absolutely top-grade journals. And moreover, other than being an excellent researcher, Anindo has always been an inspirational teacher. Since this is a webinar which will be attended by a number of students, I request all the students to listen to Anindo's lectures and watch them in the NPTEL videos available in YouTube. Personally, his lectures on symmetry and group theory, maybe above 50 or 60 lectures that he has been a joy to watch for me, especially the way he handled the orthogonality conditions arising out of Soot's lemma and the way he proved it. It was an absolute joy for me to watch. Presently, he is also teaching a course in quantum chemistry, which I believe will also be available as NPTEL videos. I ask the students to go through it and make complete use of those lectures. Definitely, it will enrich your knowledge. Okay. He is an excellent teacher and an excellent speaker. Okay. And moreover, lastly, other than being a very good academician, Anindo's human qualities have always been exceptional. He has been a very compassionate person, compassion for friends, since the days I know him from 1981. Okay, with this introduction, Anindo, I invite you, and he will be speaking on ultrafast processes in ultra-small chemical systems. Please enjoy the lecture. I guarantee you it will be a wonderful session. Anindo, the screen is yours now.
Thank you, Pinaki. I'm humbled by that introduction. It is an honor and a pleasure to not only be here and address the faculty and students of Ramakrishna Mission Belur, but also to be introduced by Pinaki, who, as he had said, has been a close friend for many, many years, from what seems to be like childhood now. So, Belur is a place that is very close to my heart, even though I have not really visited the institution ever. I've been to Belur not, but never the institution. But then we have received many, many good students from Belur. In the recent years, the stream is a little less than what it used to be. I discussed this with Devashish. I should also say Devashish is another close friend of ours. We all went to college together. Devashish was younger by 1 year, which is now, at that time in college, 1 year seems to be a lot. Junior, senior, Dada and all. But eventually we are all very good friends. Thank you, Devashish, for having invited me. Thank you, Asad, for facilitating everything. My pranam to Maharaj and everybody else on the faculty. I speak to you today from this beautiful campus of IIT Bombay, which is not only rich in facilities and manpower, but also we boast of a variety of flora and fauna, some of which you see in the background in a little shaded way. We have, I think, more than 150 varieties of birds on campus. I hope and I'm sure that many of the undergraduate students of Belur today are going to be enthused to join us as students in MSc or PhD, and hopefully some of us will join as faculty in near and a little more distant future. Pinaki, how much time do I have? Okay, what I'll do is I'll speak for maybe 40 minutes and then I'll stop. And since I don't know whether it's possible to ask questions in the middle because everybody is on YouTube, perhaps not, and I cannot see the YouTube channel. So after the talk, please feel free to ask the questions. Now, I hope my screen is visible and all. If anybody is in a position to tell me that yes, everything is okay, please do so. Asad or Pinaki or anyone. Is the screen visible? And can you hear me properly? Is everything okay? I don't hear a response, but then I'll assume everything is okay. Otherwise, just call me or something. Yeah. So now, when we talk about something like this, ultrafast dynamics and ultrafast chemical systems, first thing that we should say is what is ultrafast and what is ultrasmall. By ultrafast, I mean time in femtoseconds and maybe picosecond. Nanosecond is no longer ultrafast, we just call it fast now. But we will show you data that goes into nanosecond as well. And when I say ultrasmall, today I'm going to talk about only one aspect of our work. We work in many different systems in our group, but I'm only going to talk to you about exotic semiconductor nanocrystals. So when I say nano, I mean a particle which is whose dimension is within, say, 10, 15, well, even 100 is too much, 10, 15 nanometer, at least along one dimensions. So today I'm going to talk only about semiconductor nanocrystals, and we'll try to see why they're interesting in the first place and what we can learn about them, why ultrafast dynamics is interesting in such systems. So the first question that should come to our mind is, how do we make these measurements? I said femtosecond. Femtosecond is 10 to the power minus 15 second. Do I have a stop clock? Do I have a stopwatch that can measure time like that? Actually, we do. And that stop clock comes in the form of pulsed lasers. As you know, light is the fastest thing that we have at our disposal. Human mind is perhaps faster, but then harnessing the power of mind and all that is not within my domain. So we work with good old pulsed lasers, light. So what we do there is that we pump the system with a very, very short pulse of light. In our case, this pulse is about 50 to 100 femtosecond. Femtosecond, as you know, is 10 to the power minus 15 second. So what this pulse does is that it creates an excited state population. What do I mean by that? This is what I mean. Let us say this is a ground state of the system that I want to study. Of course, I'm drawing energies here. Okay, this is ground state. Let us say this is some excited state. What this laser pulse does is that it promotes the system from the ground to the excited state. And let me correct that. I feel very uncomfortable if I draw a bent arrow in this discussion. This arrow will be bent no matter what I do, it seems. Anyway, so what the pump does is that it promotes the system to the excited state. So there are, let us say, like Avogadro number of systems, nanoparticles, molecules, whatever. Some of them get promoted to the excited state. Remember, some of them, not all of them, very, very small fraction of them, but that is enough. Then what do? We bring in another pulse of light, equally small, equally short pulse of light, but this time, this light is white in color. The initial one, usually we use about 400 nanometer, that is blue light, the probe light is actually white light. Again, femtosecond pulse, but white light. What does the probe light do? The probe light does what its name seems to indicate. It interrogates the system. Meaning, what we do essentially is that we place a detector right here. And we monitor the intensity of the probe light. So, since it's white light, you can look at different regions of probe light, right? And you plot what is called delta A, where delta A is absorbance in the presence of pump and minus absorbance in absence of pump. Delta A is absorbance in presence of pump minus absorbance in absence of pump. Absorbance, as many of us would know, is given by Lambert-Beer's law that we study in college, which is epsilon CL. So what you need to remember here is that absorbance, unless epsilon changes or
Sir,
something,
actually, sorry to interrupt. Sir,
yeah. Go ahead, please.
আমার কথা শুনতে পাচ্ছেন?
মধ্য দিয়েই কিন্তু আমরা
Yes, I'm listening. Go ahead.
স্যার আপনার স্ক্রিনটা প্রেজেন্ট হচ্ছে না।
এই সর্বনাশ করেছে।
আপনি ওই প্রেজেন্ট বলে একটা অপশন আছে, প্রেজেন্ট অপশনটা থেকে একটু করুন। প্রেজেন্ট অপশন
এই যে স্বার্থের সমান সেটা কিভাবে
আমার তো প্রেজেন্ট ছিল শেয়ার স্ক্রিন
এবং আমরা জানি যে মানুষ
হ্যাঁ স্যার এক মিনিট
তারা কিন্তু
হ্যাঁ
সঠিকভাবে
এবার
হ্যাঁ স্যার
এই স্বার্থের সঙ্গ কিন্তু অপঘাতেই হবে।
এবার কি দেখা যাচ্ছে?
হ্যাঁ আপনি স্ক্রিনটা প্রেজেন্ট হচ্ছে না আপনার।
ঠিক আছে, তাহলে আজকে পর্যন্তই। আমরা
আমি তো স্ক্রিন শেয়ার করেছি।
না শেয়ার বলতে ওই স্ট্রিমইয়ার্ডে যে স্ক্রিন শেয়ার মানে প্রেজেন্টের অপশন আছে ওটা করেছেন তো, ওটা থেকে করছেন তো,
মানে শেয়ার স্ক্রিন, তাই না?
ফলে এখন আমরা তাহলে এবার তোমাদের কোনো প্রশ্ন?
আমি শেয়ার স্ক্রিনে গেলাম,
আমরা
তারপরে আমি বললাম অ্যাপ্লিকেশন উইন্ডো,
তাহলে আমাদের বাংলা কম্পালসারি সিলেবাস
বলে আমার পাওয়ার পয়েন্ট প্রেজেন্টেশনটা দিকে শেয়ার করলাম। এখন দেখাচ্ছে যে streamyard.com is sharing a window. I get the option stop sharing and hide.
না পিডিএফ আমি পাঠিয়ে দেবো, তোমাদের যে দুটো পাঠাতে হবে
না এখনো দেখা যাচ্ছে না, দেখা যাচ্ছে না এখনো। স্ক্রিন শেয়ারটা কোথা থেকে আসে গো?
না আমি স্ক্রিন শেয়ার করেছি।
আচ্ছা এক মিনিট,
দেখাচ্ছে স্টপ স্ক্রিন, তার মানে স্ক্রিন শেয়ার হয়ে রয়েছে।
এইটা ঠিক আছে এবার? হ্যাঁ
দেখা সি দ্য স্ক্রিন।
ঠিক আছে হ্যাঁ
এবার ঠিক আছে? So just go back and I'll say it once again. এবার দেখা যাচ্ছে তো?
হ্যাঁ দেখা যাচ্ছে হ্যাঁ।
So দেখা যাচ্ছে এখন? We're talking about ultrafast transient absorption spectroscopy. Here, an ultra short laser pulse. Ultra short means, in our case, about 50 to 100 femtosecond pulse of 50 to 100 femtosecond. Typically, we use light of 400 nanometer, creates an excited state population. So let us say this is our ground state. Let us say this is an excited state. What the pump does is that it promotes some of these systems to the excited state. What I was saying is that, of course, you would have maybe Avogadro number of systems here. Billions of systems, molecules, nanoparticles, whatever. Only some of them get promoted to the excited state. And then to understand how many have been promoted, we make use of a second pulse. This time it is a white, it's a pulse of white light. White means it has all sorts of wavelengths that you can think of. In our case, the spectrum spans from 350 nanometer to about 800 nanometer in probe. And we put a detector here. We detect the intensity of the probe light, and from there we calculate the absorbance. Absorbance, as you know, is log of I0 by IT, where IT is the intensity of transmitted light, I0 is the intensity of the incident light. Now, we measure this absorbance twice, once in absence of pump, once in presence of pump. And we calculate what is called delta A which is a pump minus a no pump situation. What does delta A tell us about? Remember, we are probing with white light. So there is a spectrum. And the typical signal that we get, if we plot delta A against wavelength or whatever parameter of energy we want, is something like this. This is essentially a different spectrum. What is the meaning of the different parts of the spectrum? Let us focus on this negative signal first. This is called a ground state bleach. What does it mean? This negative signal would typically arise in the region where you would have the normal absorption spectrum. Some of you might be familiar with absorption spectrum. Use a regular absorption spectrophotometer, measure the absorption spectrum, which is essentially a plot of this absorbance against wavelength. You get an absorption spectrum. And this is where the molecule or the material that you are studying that absorbs light, right? So what happens as a result of pumping the system with the initial blue pulse is that, as we said, you have created some excited state population, right? The other way you can think of is that you have depleted the ground state population. Let us say the ground state population was something like C0 when pump was not there. Now, after promoting the excited state population, after promoting some to the excited state, after creating the excited state population, ground state population would be something like C0 minus, I'll just write CT. So what has happened? As you know, absorbance is equal to epsilon CL by Lambert-Beer's law. Epsilon doesn't change, length doesn't change. So, but effectively, C has gone down as a result of pumping, C of ground state. So, this C minus C0 will lead to a decreased value of absorbance. So, here, this delta A, which is A pump minus A probe, is going to be negative in this region. This phenomenon is called ground state bleach. Bleach means decoloration. Okay? Removal of color is called bleach. Removal of color, in a little more technical term, is decrease in absorbance. And since we're plotting a different spectrum, you get a negative signal. This is your ground state bleach. Now, what we can do is, if you probe at different times, you see, we have written this delta T here. What is the meaning of delta T? That means that we can actually probe at different times after pumping. So, what happens? Immediately after pumping, we have maximum excited state population. That is minimum ground state population as a result of pump. So, this signal is going to be maximum in the negative direction. If I look at the signal sometime after pumping, and when I say sometime, I mean time in femtosecond resolution. How we get that? Let that be story for another day. Pinaki mentioned my NPTEL lectures. I have 4 courses on NPTEL. One on quantum chemistry, one on molecular spectroscopy, one on ultrafast laser spectroscopy, one on symmetry that Pinaki kindly referred to. So all you have to do is go to YouTube, write Anindya Datta quantum. You'll get all my quantum lectures. Anindya Datta ultrafast. You'll get all the ultrafast lectures. Anindya Datta spectroscopy, Anindya Datta symmetry. So this is how you can access all these lectures. They are available. I'll be more than happy if students have a look at those lectures. That makes me feel good. So in that lecture series for ultrafast, we have talked in detail about how to access this time scale. In fact, there are videos where we have gone into the lab, shown you the instruments, and explain how it works. Whoever is interested are welcome to see those. For now, what we are saying is that we can have a time resolution of femtosecond. We can measure at different times in femtosecond time scales after pumping, and we can plot this absorbance or the area under the curve as a function of time. When we do that, what will happen? With passing time, the signal is going to decrease, right? And finally, given enough time, it should come back to 0. Because the ground state has to be regenerated. Once your pump goes off, remember, pump is on only for a few tenths of femtosecond. After that, it is gone. So excited state, the system will not exist in excited state forever. It will come down to the ground state. That is called recovery of ground state. And this signal correspondingly is called ground state bleach recovery. And if you plot ground state bleach recovery, this actual data I'm going to refer to a little later also, you're going to get something like this. This is the time at which the pump came and created the excited state. And as the ground state recovered, the bleach recovery is also same. And we can fit this to kinetic equations, and you'll see what kind of information we can get about the system. So this is one part of the story. The other part of the story is that you can also get positive signals. What is the meaning of positive signal? Delta A, that is A pump minus A no pump, is positive. So here we are actually monitoring an absorption by the excited state, not the ground state. Okay. Here the probe wavelength is such that it is absorbed by the excited state, not by the ground state. So what happens? Before the pump comes, there is no excited state population. So absorbance is zero. The moment you create excited state population, you're going to see a positive signal like this. And then with passing time, what will happen? This positive signal will also decrease and it will become zero like this. This is called transient absorption, and it's going to decay like this. If the decay is fast, you'll see the decay will be complete within the time window of your measurement. If it is not fast enough, you'll see it will not recover completely. We'll have more to say about that later. But this is a very quick run through of the kind of experiment that we do, the kind of data that we get, and the kind of analysis that we can do. And this is the instrument that is required to perform experiments like that. We have switched to the laser pointer now. What you see here is a very powerful ultrafast laser. It is called an amplified laser because, okay, I can use this. Yes, sir. Forgot all about this. So this is an amplified laser which gives us about 50 to 100 femtosecond pulses, and energy per pulse is about millijoule. What you see here, the white box, this is called optical parametric amplifier. From this, we can generate many different colors. The output of this is 800 nanometer. And then the output of this is fed into, this is this spectrometer. So I'll not go into the detail of this, but all I want to say is that this is where we keep the sample, and these two are the two detectors at which we measure. This is a retroreflector mounted on a 1 foot long screw. If you want to know more about this, feel free to see our NPTEL lectures. Okay, so this is the spectrometer by which we do the absorption studies. Another kind of experiment that we do is by fluorescence, something similar. We excite the molecule by a pulse that it of a wavelength that it absorbs, and we monitor the time evolution of its fluorescence, and we get decays like this. For that, this here is the instrument. Two kinds of instrument. If you want to measure in nanosecond time regime, then we use a technique called time correlated single photon count. Very ubiquitous. Many people use it now. This is a compact plug and play, what has become a toy, that kind of instrument. When I was a PhD student, this was not a toy. And if you want to do fluorescence experiments in femtosecond time regime, then the technique that we use is femtosecond optical gating. Here again, we have a laser. This is a little old setup. We have been using this since 2008. So this here is a laser which gives us 100 femtosecond pulses, but much less energy per pulse. And this is the spectrometer in which we do the actual measurement. You can see this beautiful blue and red and green colors. The blue is what is called the second harmonic of the laser. Green is the actual fluorescence from the sample. Again, more about this in the NPTEL lectures. The system that I want to talk about today are semiconductor nanocrystals. And these are a little weird because nanocrystals don't behave exactly like atoms, don't behave exactly like bulk material. And the difference stems from the fact that, well, something that you have been studying or you have studied already. You know molecular orbital theory, don't you? You know that if I have a molecule, then I can have this atomic orbitals participating in linear combination to give us what are called molecular orbitals. And molecular orbitals have a wide separation and they are very discrete. What happens in solids, the band theory that I understand most is that there is a large number of participating atomic orbitals. So the linear combination has many, many terms. So these molecular orbitals come so close together that they form a band. The antibonding orbitals come together to form the conduction band. The bonding orbitals come together to form the valence band. And you cannot really distinguish between the levels that are there in these bands. But if you start breaking down this material, and I'm talking about semiconductor material here, you start breaking this down, you reach a regime, say when you're in some tens of nanometers or so, less than 100 nanometer, where you form what are called quantum dots. So here you still have bands, but the number of atoms is so small that within the bands you can see these energy levels also. So this is the kind of system that we seek to probe because they are actually of a lot of interest. You might, some of you might have seen quantum dot televisions. So these quantum dots are essentially semiconductor nanocrystals. Many applications now. So this is what we want to probe, these energy levels within these valence and conduction bands. And this has been studied extensively over the last 20-25 years. And it has been established what kind of energy levels are there. See, what happens is that when you promote an electron in a solid material, the electron goes here, and the vacancy that it leaves here, as all of us would know, is called a hole. The hole is sort of like the complement of an electron. So let us not worry about the nomenclature and all here. Once again, we have discussed this in a little more detail in these lectures. But all I want to say is that the absorption spectra of systems like this, semiconductor nanocrystals, are very, very well characterized. It has been established and it is very well known what kind of structure we have in these semiconductor nanocrystals. So what we are interested in is what happens to these excitons. Well, excitons, let me say that. I said that we create this electron holes, right? For every electron in the conduction band, we could have a hole in the valence bond. And this electron and hole together is called an exciton. An exciton is defined as a tightly bound electron-hole pair. So what would happen? You excite by a pulse light. The light is on for a very small time, then it goes off. What happens afterwards? First thing that can happen is that this electron can recombine with the hole. And recombination can be of two types. One in which light is emitted. This is called a radiative recombination. And the other is recombination that does not involve emission of light. That is called non-radiative recombination. Again, this is now textbook material. We will not delve too much into it. Whoever is interested, there's plenty of material in the literature where you can learn more about this, even Wikipedia. But it is not so simple. It is not as if we create an exciton and then the electron and hole combine, light is emitted or not emitted. That's not the only thing that happens, thankfully. That is why these systems are interesting to study, and that is why there are plenty of applications. See, what happens is you have some crystalline structure, right? Cations and anions. Let us say something like this. So when you make a nanocrystal, what happens is that in the middle of the crystal, the crystalline structure is very nice. What happens in the at the surface? The structure is broken. So you have things like dangling bonds. You have things like defects. I think you know about say Schottky defect, Frenkel defect, all these things. So these defects are there in large number, especially in nanoparticles because they have large surface area. These defects serve as electron traps and hole traps. Electron trap means these defects can the electron can migrate to these defects. The structure, chemical nature of the defect is such that it can take up an electron. Then what happens? Separation of electron and hole, and then you have a long-lived electron and hole pair. Or you can even make use of this trapped electron for applications as in solar cells or in photocatalysis. Hole traps can also be there. The chemical structure of the defects can be such that they trap not electron but hole, and same effect is there. Okay. This is the band structure. The reason why they are parabolic is that energy of these bands is conventionally written in terms of k vector, and it is something like k. So k is momentum, right? As you know, energy would be kinetic energy, momentum square divided by mass. That is what gives rise to this kind of a diagram, and that is what gives rise to your effective mass of electron and hole that you can calculate from this parabolic relationship. So what can happen here is that you create this exciton. Now the electron can be trapped. And electron can be trapped in two ways. See, I said we pump by 400 nanometer light. That is in the blue end of the spectrum. It is not necessary that the band gap is 400 nanometer. Typically, band gaps can be much less than that. So if we do what is called above band gap excitation, then we create what are called hot electrons. That means electrons that are more energized than they would have been if they were at the band edge. Right? This is your valence band, let us say. This is your conduction band. If the situation is like this, the electron is right here at the lowest possible energy level of the conduction band. The hole is right here at the highest possible level of the valence band. Remember, hole has to be up to have lower energy. Then this is the most relaxed situation in which you can prepare the exciton. This is a relaxed exciton. If the situation is rather like this, where the electron is at a higher energy level than at the band edge, the hole is at a lower energy level than band edge. Lower energy level for hole is actually higher energy. Then you create an exciton which is hot. So these hot electrons can be trapped directly by the traps. Or they can first relax and then they can be trapped once again. This relaxation is called intraband relaxation. The same thing can happen with holes. Okay, so you can hot electron trapping and cold electron trapping. Another very interesting thing that can happen when you do above band gap excitation is that you create more than one exciton. Then one electron, after all, this is an energized electron, right? They want to come down to the excited state. But one of these electrons can actually transfer the energy to the other one. This is called Auger recombination. And now this electron can be promoted once again. So these are all different things that can happen to the exciton before exciton recombination can take place. And that is what determines many properties of these nanocrystals. So I'll talk to you today in the remaining time that I have actually lost track of time. So Pinati or somebody, please remind me, say 5 minutes before when I should stop. So I want to talk to you about two systems that we have studied over the last 5-6 years. One is these nanotetrapods, very good looking, right? All chemists would be excited to see tetrahedra. So these are nanocrystals prepared in the shape of tetrahedra. And the other thing that we talk about is water-soluble spherical nanoparticles. So our work on cadmium selenide nanotetrapod studied because of the interest of an MSc student. This was Ashutosh, an integrated MSc student in our department. At that time, he used to work only on molecules and silicon nanoparticles. But he said, no, sir, the semiconductor nanocrystals are very good systems. Let us work. But I did not know anything about nanocrystals at that time. So we collaborated with a good friend, Rohit Srivastava. He is now presently head of our bioscience bioengineering department. And Rohit and I guided Ashutosh to his MSc project. And he kickstarted our work on cadmium selenide nanotetrapods. This work was carried forward by my PhD student, Shucheta. Shucheta has graduated. She's got her PhD degree last year, and she has joined this postgraduate college in Pune. She is now an assistant professor. We received very useful input from another PhD student, Balagopal Mattala. And right now, the work is being carried forward by my student, Faryad. And Tanuja has also contributed to some extent to this work. So this shape, other than being interesting to chemists, is very attractive for many different reasons. It can serve as building block for inorganic dendrimers. It has been shown to provide mechanical strengthening of polymers. It has been proposed to be used in fluorescent biosensing, and it is proposed that it can have very useful applications in photovoltaic devices. It can applications in solar cells. So first of all, we wanted to learn to make them, and we wanted to study them. Preparation is by a very standard method. We have to modify it a little bit, but it is by something called hot injection method. We'll not go into it today. But it's a one-pot reaction by which one can prepare it with a little bit of practice. And this is the electron microscope. This is what it looks like under an electron microscope. you can see that we do have nanocrystals. Right now, I'm showing you only one kind of nanocrystals. Size of these arms and thickness of the arms, they all depend on how long you have done the reaction. In the nanocrystals that we are presenting, you see the diameter of the arm is about 2.6 nanometer, and the length of the arm is about 8 nanometer. So pretty big nanocrystals. We actually want to work with smaller ones as well. Now we prepared them in two ways. But before that, let me show you this mandatory photograph. As we do a reaction for different time, as the arms grow in length and in thickness, you see the color changes. The color changes because the energy gap in nanocrystals is determined by and large by the size. It is governed by a modified particle in a box kind of model, and that is why this is something that is ubiquitous. Anybody who talks about nanocrystals, semiconductor nanocrystals, would show you a photograph like this. Now, we prepared these nanotetrapods in two ways. One in which we used a glove box to prepare the precursors. A glove box is something that gives you a very protected environment, no air, no moisture, that kind of thing. And another one in which we are less careful. We did not use a glove box. When we are less careful, we get things like this. You get dual emissive nanotetrapods. Dual emissive nanotetrapods are attractive in their own right, but they're problematic as well, because this broad emission that you see is because of trap states. Now, when we use a glove box, then this trap emission is suppressed. That means we have prepared better quality nanotetrapods where you don't have so many defects. And you see there is a huge increase in the emission quantum yield. Emission quantum yield of this, what is called this bandage emission, was 0.003 initially. When we use a glove box, we get 0.06. So an order of magnitude improvement. And we look at it in the time domain, you see the photoluminescence decays, first of all, by and large within 80 picosecond or so. But there is a long component as well. Because of this long component, you see the photoluminescence. But what we see is that if there is no trap and if there is no trap, if you compare these two situations, the slower one, the upper one, is in no trap situation. The lower one is in presence of trap. And we worked out the time constants involved. The major time constant is of 8 picosecond. In case of the when there is no trap, in presence of trap, we get an additional 1 picosecond component. So this 1 picosecond component is associated with trapping. Trapping is associated with a rate constant of 1 picosecond. That's what we are saying. But then, these quantum yields are very bad. Even when there is no trapping, quantum yield is as low as 0.0006. Nobody would take that seriously. So, let's not talk about this part right now. But what is heartbreaking here is the extremely low PL quantum yield. So we thought that the reason why we have low PL quantum yield, PL means photoluminescence, the reason why we have low photoluminescence quantum yield is traps. Can we convert that to an advantage? Can we introduce some defect? And as a result, we get strong emission? Again, this technique is nothing new. Narayan Pradhan, for example, in Indian Association for the Cultivation of Science, has performed seminal work in this field. So learning from Narayan's work and from Professor D.D. Sharma's work and from many other people's work, what we did is we tried to impregnate our nanotetrapods by copper. And copper means copper 1. Copper 1 is a good hole trap. Right? It wants to trap holes and become CO2 plus. So we were successful in, so this is Faryad's work. What I was talking to you about earlier was mainly Sucheta and Ashutosh's work. So we are able to prepare nanotetrapods. Some of them get broken. Nanotetrapods that have copper doped in it. And as a result of doping, what we see is that we get very strong emission, which is red shifted. And this is due to this defect that we have introduced knowingly. So defects are a problem. But then you can actually engineer defect states to get what you want. Next, we wanted to see if you're going to talk about, okay, once again, I'll skip this because I'm running out of time, I'm sure. Next thing that we wanted to do is we wanted to see if we can take these nanotetrapods in water. Because you want to talk about applications in biology, you better work in water. So what we did is these tetrapods are actually capped by some agent. The capping agent that we use in the studies that we showed you earlier is oleic acid. So we did a ligand exchange, very simple process, by mercaptopropanoic acid, MPA, and that makes the nanotetrapods soluble in water. We were successful in doing that. Unfortunately, once again, we were heartbroken to note that the moment it goes into water, it is no longer photoluminescent. Well, we could still propose some proof of the concept kind of application. We found that these nanotetrapods in water denature proteins. And knowing that human serum albumin, for example, is a carrier protein that can bind a lot of drugs, we did this proof of concept study in which we bound warfarin, which is a model drug, to human serum albumin, and we could show using time-resolved fluorescence that we can set it free by adding these water-soluble nanotetrapods to this warfarin-containing HSA in water. So maybe one can think of a drug release mechanism using this, but let me tell you that this is in a very, very preliminary stage right now. It is not easy. There are hundreds of obstacles associated with this. But one good thing is that we could publish this in ChemPhysChem. This is a special issue of ChemPhysChem and European Journal of Organic Chemistry and European Journal of Inorganic Chemistry published together, a virtual issue, to highlight our Department of Chemistry, IIT Bombay. So it's a matter of pride for our department that we got highlighted in these 3 Wiley journals. I guess edited it, and it got published sometime last year. So that is one thing that I wanted to highlight as well. But while we were doing all this work, and we found that, okay, we are able to prepare water-soluble quantum dots, but they are not photoluminescent. All this time, we have this excellent PhD student, Sharmishta Das, and a very, very gifted postdoc who has now completed his tenure here and is going for a second postdoc to Italy. Somodipta Rokkit. Somodipta did his PhD from Jadavpur University. Excellent. He's the best postdoc I've ever had. Very highly motivated, very highly efficient. He did a great job when he was here. He's going to be, I'll show you one of his papers. He's going to be a very important author in several of our publications in the next 1 year or so, even though he's now completed and he's going. So what they did together is that they prepared these PEI cap cadmium sulfide quantum dots. These are spherical quantum dots. PEI means polyethylene imine. And again, this is a one-pot reaction, standard literature method. They could prepare this. And then this is what you see under the microscope. You see this kind of structure. This is what you would have perhaps seen when you studied Black's law. I'm talking to undergraduate students now. So elders, please excuse me. This kind of a structure tells us that we have very nice crystals. And these are nanocrystals. This is the size distribution once again, less than 5 nanometer diameter crystals. So very well-defined crystalline plane. Average diameter is 4.84 nanometer. This is what we are able to prepare. And again, if you remember the absorption spectrum I showed you from literature, we get a similar structured absorption. And Sharmishta did an excellent job of assigning each and every band to a particular transition. What is heartening here is that, first of all, this quantum dot is prepared in water directly, not prepared in oil and then transferred. And see how strongly photoluminescent it is. This is a photograph of this quantum dot dispersion in water in UV chamber. Excitation wavelength is UV, and photoluminescence quantum yield is 0.36, which people talk about much higher quantum yield, but 0.36 is very good. So this is this emission spectrum, very broad, and you can see the color that is there. I'll not risk telling you what color it is because I'm colorblind. You can figure out what it is. All right. And here we see that we have a very long PL quantum yield, even though there is an ultrafast component also. But the visible PL that you have is because of this quantum yield, and radiative trap states are involved in this strong photoluminescence. Now, what Sharmishta did, and this is a beautiful piece of work, is that she looked at the transient absorption data. You might remember that I showed you something like this a little earlier. I'll not really go into the intricate detail, but I'll give you an overview. So what she did is she looked at this data and tried to make sense of what all is going on after rebound. So first region that she looked at was this ground state bleach. You might remember negative signal is ground state bleach. And this bleach signal is dominated by electrons. And many things contribute to the recovery of this signal. The first factor is electron trapping. And you might remember that electron trapping can take place in two ways: hot electron trapping and cold electron trapping. So by a careful analysis of this data, we could figure out that intraband relaxation takes place with a time constant of 380 femtosecond. Hot electron trapping is associated with a time constant of 1.2 picosecond. Cold electron trapping is a slower process that takes place in with a time constant of 11 picosecond. Okay. And an evidence of hot electron trapping is that if you change the excitation energy, if you delta E means how far away you are going from the bandage excitation. If you increase by too high an energy, there is a drastic fall in photoluminescence quantum. Why? Because if you promote higher and higher, more of hot electron trapping will take place, and that is an efficient process associated with a time constant of as small as 1.2 picosecond. So this is how we understand what all goes on post pumping, post creation of the exciton dynamics. But this is not all. Another thing that takes place is multi-excitonic Auger recombination. This also, you might remember, we have said if you use high enough pump energy, then you end up creating more than one excitons. And these hot holes, hot electrons, can sort of exchange energy. So one gets deactivated, one gets promoted. Again, by a careful analysis. So by careful analysis, I mean you have to write all sorts of rate equations. All of us have studied chemical kinetics, same kind of thing. So see, the skills that you learn during BSc or MSc are absolutely useful when you do research. All we do here is that we write schemes and we write your chemical kinetic equations, and we try to find out the time constants, rate constants. So the rate constant that we get for the Auger recombination is about 29 picoseconds. And the interplay of all this is reflected in this ground state bleach recovery. All right. So far, we are talking about this strong negative signal. There is something else here which is very easy to miss, and it is this kind of photo-induced absorption signal. This is often called the shelf signal. So you see, here it looks like baseline, isn't it? It looks like zero. Doesn't look like anything is there. So if you just neglect it, you'll not be blamed. But actually, it is not zero. If you zoom in, you'll see a structure like this. Again, very small signal, but we have been successful in analyzing time evolution of this signal as well. And this signal is associated with holes. What happens is, okay, you create the exciton once again. We are talking about electrons so far. Now let's talk about holes. The probe light can actually probe holes as well. As I said, hole trapping can take place, and that is ultrafast. It's well known from the literature. If the probe light is of sufficiently small wavelengths that it can look at this promotion of holes, then we get a positive signal, photo-induced absorption, decay of which gives us an idea about hole relaxation. And once again, this signal is dependent on how intense your light is. So this analysis was also done, and a conglomeration of all this is that we could figure out exactly what is going on. You create the exciton, then intravent relaxation is associated with 0.38 picosecond, hot electron trapping 1.2 picosecond, cold electron trapping 11-12 picosecond. I don't know why I've written 11 here and 12 there, but well, sorry about that. Then there is a longer one also. Deep trapping is also there, 129 picosecond, and Auger recombination is something that takes place with a time constant of 29 picosecond. Right? So this is what we published very recently in Journal of Physical Chemistry C. Now that we understand what happens, can we think of some application? So one application that we're thinking about is metal ion sensing. As I told you, it is strongly photoluminescent. Can we sense metal ions? This is of potential use in studying things like water pollution. As you know, you don't want lead in your water. You don't want mercury in your water. So if you can detect how much lead is there in your water, that is the first step of tackling the problem. But when you do that, you want this technique to be selective. If this photoluminescence is to be quenched by a metal ion, you want it to be quenched by lead only and nothing else, mercury only or nothing else, something like that. And what we are focusing on right now is, can we understand the mechanism of action? Because many processes can be involved. Surface modification is a very important thing, as I'll show you. Charge transfer can be involved, energy transfer, many things. So what we see is that we try to add metal ions to these PEI coated, PEI capped CDS quantum dots. Absorption spectrum doesn't change. We're happy about that. When we look at photoluminescence, we see that photoluminescence also doesn't change except for lead. This bar chart shows you how the PL quantum yield, photoluminescence quantum yield, decreases drastically only with the presence of lead and nothing else. So we're very happy about that. We have selectivity, we have ion sensing. Now we want to know why is lead and what all is happening. This is the photograph that shows you, in absence of lead, you get strong photoluminescence. In presence of lead, there is no photoluminescence. All right. So once again, we look at photoluminescence. You can see that it has become faster in presence of lead. But the more interesting thing that happens is when we try to understand our pump probe transient absorption data. So this is a cartoon of section of the quantum dot that is capped by our polymer, PEI. So you're excited, it is strongly photoluminescent, fine. Now, it is known that when you take cadmium sulfide and you use PEI as capping agent, the cadmium atoms are passivated very nicely, right? Cadmium and PEI like each other. Sulfur is not passivated very nicely. So it can be dislodged by something that comes in and pushes it a little bit from the surface. And this nudging, pushing away from the surface, you can try to do with metal ions, right? Now, there are two kinds of metal ions. The way we have shown it is that we have two kinds of metal ions. One is lead and the other is everything else. Well, there's a reason for doing that. Let us say I have a metal ion that binds very nicely to PEI. PEI, remember, is a polymer. So if PEI can bind this metal ion nicely, what happens is that it does not even reach the surface of your quantum dot. It gets trapped outside. Okay? I want to go to, you're set out from your home to go to your college. In the local tea shop, your friends are sitting. You like them very much. You start talking with them, you don't reach college. That is what happens with metal ions that bind nicely with PEI. Now, lead turns out to be unsocial. No friends in tea shop. So lead does not bind well to PEI. So it sort of nudges its way all the way to the surface. And when it does that, it encounters this weakly bound sulfur. In any case, lead is a little bigger. So it pushes sulfur out of it and creates fold trap. And signature of the fold trap is in this signal, in transient absorption. Remember, I told you that this shelf region, positive signal is because of holes. When we have lead, we see that this signal is stronger, which means more holes are being created post-excitation. Okay, I'll not talk about this. We can do we can create a Langmuir kind of isotherm from our transient absorption data, and we determine the value of the binding constant to be very, very large, 10 to the power 4 per molar. Now we have created the excitation. Fine. What happens? Hole trapping takes place in less than 0.2 picosecond. Electron trapping, now that we have lead, it will attract the electrons. Electron trapping, we found out, takes place with a time constant of 6.2 picosecond, and that is the source of quenching. Okay, so electron hole both are trapped at the surface and they can recombine, and that is why PL gets quenched. So this, in summary, is what happens, and this is the mechanism of selective quenching of photoluminescence of the quantum dot by lead. Well, so I've told you about two kinds of things. I'm sure it has been very rushed, but I'll definitely not talk about the rest of the thing that I have in the slides. Rather, let me close with thanks to all the students who have been in our group, postdocs, collaborators, funding agencies, our institute and department, and thank you all for being here. Thank you for listening. I'm done.
Hello, sir. Hello.
Yes, yes, Asaf.
Hello, sir. Thank you so much, sir, for this lovely talk. Thank you so much for giving us your time and this nice talk, sir. It's really very advanced level talk that we enjoyed. Thank you so much, sir.
Thanks. Pleasure being here.
Thank you, sir. So I like to introduce, sir, next speaker, Pinaki, sir. Yes, sir.
Can we take a few questions from students? Is there any provision for that in StreamYard, or they can't? I mean, since
No,
they're listening in
StreamYard.
YouTube.
We have to go to the YouTube then, actually.
Okay.
So,
Is it possible, or I mean, if we are running behind schedule, then maybe we'll skip that. I mean.
okay, maybe you can skip that, sir. We can have
Okay.
discussion among us, sir.
Okay. Okay. Thank you, Anindo, for a very nice presentation as always, and good to see you.
Good to see you as well.
Okay, Asad.
Asad, what do I do now? I'll click Leave Studio, right?
Okay.
Yes, sir. Yes, sir.
Do I
Yes, sir.
click Leave
Thank you
Studio?
so much, sir.
Thank you.
Okay, Asad. I am also clicking the Leave Studio. Okay.
Okay, sir. No problem, sir. Thank you, sir.
Okay.
Thank you.
Thank
Sir.
you.
So I'll request the organizer to put Niladri on the screen. And now we are going for our next talk for Niladri Patra. Hello, Niladri, are you there? Niladri, maybe some technical issue, probably. Hello. Anyway, I'll introduce Niladri Patra. He's my friend from IT Delhi. We spent a lot of memories together. Niladri, complete. Hello, Niladri. Sorry, probably some technical issues going on here. Probably some net problem.
Hello.
Hello, Niladri, are you there? Niladri?
Yeah, I'm here, but do you hear me? I mean, I'm audible?
Yes. You're
Okay.
very clearly audible. Okay. So I like to introduce my friend Niladri Patra. Niladri did his BSc in 2006 from Calcutta University, Rohada Ramakrishna Mission, then moved to IT Delhi. And in 2008, he completed his MSc, and then in 2013, he completed his PhD from University of Illinois, USA, Chicago, with a joint collaboration with Harvard University. Then he did his first postdoc in 2015 from MIT, Massachusetts Institute of Technology, and did his second postdoc in 2017 from Brookhaven National Laboratory in New York. From 2017 to into the present, he's working as an assistant professor at IIT Dhanbad. His mainly research area is nano assembly, the nano rods and nano surface morphology of nanoparticles in chemical and biological system. He also trying to develop a molecular dynamics software and also working on protein and enzyme interaction and calculation and finding out the binding interaction between them. So I'd like to invite Professor Niladri to give us his talk on nano assemblies. Please, Niladri, share your screen. Thank you so much, Niladri, for being with us.
The screen is visible. I don't see it here
No.
yet. Oh, that is weird.
Yes, it's coming. It's coming. It's coming.
I think the internet actually, I'm sorry for the internet.
Yes.
CPW had made a mess. They are trying to upgrade the internet, and we spend huge amount of money. It's almost 10 crore. And they did something unusual. They could not figure it out. So I don't still see the screen. Do you see the screen?
Yes, we can see the yes. It's coming. Yes, molecular modeling. Yes, coming.
So it's now clearly visible. The whole screen is visible. Only the slides are visible, right?
Yes, full screen are visible. The slides are visible. You can go on.
So I can start, right?
Yes.
Okay. So thank you very much for giving me the opportunity to present the research work. And I'd like to thank the Department of Chemistry of the Vidya Mandir, and also I'd like to thank the organizers and Maharaj. Since majority of the students are undergrad, and my research my research actually mostly theoretical and computational. I will skip mostly the mathematics part and the algorithm part. So what I'm going to do today or talk about mostly the phenomena. Okay, so I'll focus on the phenomena, so that will give you the flavor of how we can do research using some advanced methods to understand some of the natural problems. Okay, so we actually use multiscale model for self-assembly of nanostructure and nanomedicines, as is evident. So we'll be talking about first some material self-assembly, which I did in postdoc and in PhD. Later, I'll talk about mostly the biological problem, the protein and other stuff that we have been doing from the postdoc and as well as in my research group. Is audible, right? Hello? Is that audible? I'm audible, right? Hello? Hello? Do you hear me? Oh, there's something wrong. Hello? Hello? I don't see any response. Okay. So we can, I can go ahead. Okay. Okay. And then we'll talk about how we can use the dendron-based micelle for the drug delivery system. And we'll also talk about how we can use the lipid system as a drug delivery carrier. And then finally, we'll talk about some of the complicated systems. This system is actually called catechol methyl transferase, which is basically an enzyme which is responsible for the Parkinson disease. And then finally, what we are doing in our IIT, we'll talk about some efflux mechanism. Since nobody has probably idea, especially I'm talking about the students, about what is the molecular dynamics method. Primarily, we use molecular dynamics method to understand the physical phenomena or sometimes the chemical phenomena. So it's nothing but what you do in molecular dynamics. You keep the atom and the molecules are allowed to interact between themselves, and then you keep a note about their positions and the momentum. And you know that from the classical mechanics, if I can have the positions and the momenta, then in principle, I can calculate any property or any thermodynamic property from those Q and P using the statistical mechanics. So that's the trick. Okay. The trick is in molecular dynamics, you generate Q and P over the time, which is sometimes called dynamical evolutions. And where you record it, the record is called the trajectory. So from the trajectory, you use statistical mechanics to get the thermodynamic data. And the dynamical evolution over the time, In order to do that, you need some kind of mathematical formula so that you can generate these dynamical evolutions. And the simplest theory or the simplest equation by which you can generate this Q and P is nothing but the Newton-Chicken law. Okay, there are some other equations. There are some modified equation, Newton's law. Mostly here we'll be using Newton's law, and then some modified Newton law, sometimes called Langevin dynamics. Okay, so it's not complicated. It's a very simple thing. Initially, you need the initial coordinate, positions, and the momenta, and then you need a potential by which you can get the force. And if you remember, if you see these simple equations, you need the force. Okay, so in order to get the force, you need a potential, and that potential you have to devise from the very beginning about depends on the system. Okay? Either it is a classical force or quantum force. When we use the classical force, sometimes it is called force field, then we call the classical molecular dynamics. And when you use the quantum thing, that means when you want to do some chemical, when you want to study some chemical phenomena, you need to have the Schrodinger equations. And then we call this is a quantum molecular dynamics. So based on the force, how you calculate the force, you divide the molecular dynamics in a different way. Sometimes classical, sometimes quantum, sometimes classical and quantum in a mixtures. This is called the hybrid quantum molecular dynamics. But primarily, we'll talk about first the classical molecular dynamics, and then as you go along, we'll talk about the hybrid system. Okay? These are the equations. I'll skip. If somebody asks or needed, then we'll discuss about these methods. Okay, so what is this about? So initially, what we wanted to do, we put two actually droplets. Okay, we put two droplets on a relaxed graphene, and then we start to simulate the system, and then we see that there is a dent. Okay, there is a dent on the graphene sheet, and you see that the water droplet actually not sitting on the top of each other. Okay, when the graphene is fixed, they will sit on each other. But if the graphene sheet is relaxed, they will not sit on each other. This is because they want to enjoy the dent. Okay, so once the graphene is dented by the van der Waals force, actually, and the electrostatic force between this water droplet, basically, it's a balance between this bending energy of the graphene and the van der Waals and the electrostatic between the water droplets. The equilibrium positions in something like this. Okay, so now once we know that water has a capability to dent a graphene sheet, can we design a nanostructure using this droplet, or rather water droplet or any other droplets? Okay, so we extended this idea something like this. So we make a flake. Okay, so there is a reason why we have this kind of flake. So what we wanted to do is here, we design a flake in such a way, and then you put a small droplet, and then as we go along, you see that this nano sheet actually have this kind of structure, and the water which was inside, as you can see in this B, actually now it is outside. This is because the graphene-graphene interactions, which is actually in this case hydrophobic, is higher than the graphene-water interactions. Okay, so water is actually acting as a catalysis. Okay, so initially the water in the graphene, they actually interact each other something like this. But once the graphene can see the other graphene sheet, then water has no role. Okay, then it will just spit out the water, and the graphene-graphene interaction is much higher than the graphene water, because this is the hydrophilic interactions. Okay, similarly, you can design a storage system using water droplet, as you can see on the movie. Okay, on the right hand side. So you design this some kind of flower, you fix couple of atoms, then you put a small droplet, and you can see that the van der Waals interactions, okay, and they basically close it. And if you wait for a very long time, okay, then what will happen? This water will disappear as a gas, okay, and then you can lift up only with this closed vehicle system. This can be used for some vehicles for the delivery of some materials inside in a system. Then what you do, then we want to understand, okay, so what are the control force? If we know what are the forces are acting on the system, so you can control. Okay, so in the self-assembly, there are different ways to do it. Okay, the most important part is to understand the system, what are the forces. So once you know what are the forces are acting on the system, then you can play with it and you can control it to devise or to design a different nanostructure. For example, in this case, you have a long graphene nanoribbon, and then you put a small nanodroplet on the tip. Okay, and as you see, these are the dynamical evolution of this type. Okay, so this small nanodroplet is not good enough. It's not big enough to hold the tip. You can see that the tip is not actually attaching. It's not attached on the surface. Okay. So what happens is once it is here, then it is convey hesitance. Okay. Also in the movie. So basically now you have a sliding movement. Okay? It's basically slides. But now this graphene actually see the other side of the nanotube. So basically it has an advantage graphene. So now this is a equilibrium structure. Again, if you wait for the long time, the water will disappear the water will not be liquid because this is a gaseous simulations. Okay, it's a NBT simulations. So the water will disappear as a gas, not to be liquid, and then the structure will be like this. It's like a knot, not like a knot. It's a sliding structure. But what happens if we increase the size of the nanodroplet? Okay, so in this case, actually, you can see that the water nanodroplet is large, is very large compared to the other structure. Then you can see that this nanostructure, this nanodroplet is good enough to hold the tip. So then what happens is not sliding anymore, it is rolling. So by controlling, and actually just to tell you that the width of the ribbon is same in both cases. Only the length is different, but the length has nothing to do with the sliding or the rolling. Okay, so we increase the size of the nanodroplet or radius of the droplet, then we see we have a different nanostructures. Actually, there are some mathematical model and some analytical model too, but I'm not going to discuss all these things here. But just in a phenological way, we can just so it can roll it on the bit. But if you have a smaller droplet, it's not good enough to hold the tip. And then once it sees the joining point, it will slide, not in the roll. And you can see the movie. Okay, I'm going to start the movie. Oh, what happened to the movie? Look at this movie, the simultaneous movies. If you have a small nanodroplet, it's basically sliding. So the important part is when it is attaching to the tip. So now here, look at the first structure, the top one. The water nanodroplet is not good enough. Okay, and you can see that the distortion of the water droplet, it is not spherical anymore. It basically distorted by the pressure or by the interactions of this graphene. So one more time, you see that. And you can see that in the now for the lower part, you can see that the tip of the nanoribbon is always on the surface of the nanodroplet, and then it consists. Actually, when the graphene actually see the sliding mode on the rolling mode, it's same because this is still the graphene interactions. Okay, so by controlling the size or by changing the size of the water nanodroplet, even the width of the nanoribbon is same, you can get two different nanostructures. Basically, now you can control the self-assembly of the graphene nanoribbon by changing the water. Again, I'm just reminding you that the water is acting as a catalyst. It is just helping you to overcome the bending energy of the graphene nanoribbon. Okay, so the bending energy, which is basically a positive energy, because graphene doesn't want to bend it. Okay, but here the advantage energy or the negative energy, in the sense, we can call the graphene water interaction energy. So think about a curve, and then this activation energy, or we can call the whatever you call it, the activation energy, it has to come from the graphene water energy. But once is the other side, once the graphene tip sees the other graphene or the other part of the graphene, then water has no role virtually. Then it can roll it by itself. Okay. So then we introduce more complexity in the system, because water actually you cannot have control. You can only control the diameter of the water. But can we have a different substance rather than water, which can have a more features? For example, nanotube. In a nanotube, you can control the diameter of the nanotube. You can control the what is sometimes called NM or chirality of the nanotube, or you can change how you put the nanoribbon on the nanotube. Either is in the top or is in the inside. Can we have a different structure? Okay, so let's see. You can see that if you put the nanoribbon on the nanotube perpendicularly, it has a rolling structure. Okay, it has a rolling structure. Again, here the graphene interaction energy is basically the driving force. That is the thermodynamics. Okay, And but if the nanotube is very small, think about like 1 nanometer or 2 nanometer, then the bending energy of the graphene nanoribbon is extremely high. So if the nanotube is larger, or sometimes if it's more than 10 or 15 nanometer, then it is easier for the nanoribbon to roll. Okay, so here the activation energy or the positive energy or the bad energy you can call, it is about the bending energy. Okay, then the bending energy depends on the diameter of the nanotube. If the nanotube is big, then graphene nanoribbon is very heavy. But if the diameter is very tiny, or like less than 5 or 8, actually we have a phase diagram, but I just keep all this. We actually calculated that if the nanotube is less than 5 nanometer, it will not roll. Simply, it will not roll because the bending energy of the graphene nanoribbon is too high. The graphene interaction energy cannot compensate that. Okay? And the second type, if you put this graphene ribbon slightly tilted, then you can see that you can have a helix structure. So you can think about it. Depends. So these are all kinetics. Okay, these are all kinetics. These are all non-equilibrium structure. So not only depends on the diameter of the nanotube, it depends how you initially positions on your graphene nanoribbon on the nanotube. So you can have a different nanostructure, depends how you control it, how you position it, what are the chiralities. Similarly, you can also generate different nanostructure inside the nanotube. For example, if you put a nanoribbon inside a nanostructure, you can have this kind of structure. You can see that this is a first step, and if you put it, eventually it will form a helix inside it. So here, what you do, the inside structure is more complex rather than the outside. Okay, so I don't have enough time to discuss all this, but we can discuss a little bit. Actually, after the simulation of more than 1 year, they actually found experimentally that it's actually graphene nanoribbon can exist inside the nanotube, although the structure is a little different. Here the rolling is in a different way, and here it is different. It is like a twisting here, but this is not twisting. This is just a rolling inside it. Okay, but again, it can happen. It can happen. You can generate a structure. Even if you put a double nanoribbon inside a nanotube, you can have a double structure like a double helix. And the interesting part is, if one of them is left-handed and the other can be right-handed, it cannot overlap. This is so interesting. In fact, I don't think I have it here. Let me explain this one. Then I'll talk about the complexity of the system. So if you put the nanoribbon from the right hand side, and you can see that it is actually going outside the left hand side. This is because of the momentum. Okay, this is because of the momentum. It's just a kinetic energy, the potential energy, nothing but. But at some point, it will come back and make a roll. Okay, now this is because there is no advantage if the graphene ribbon is outside the nanotube. It always wants to come inside so that it can enjoy the graphene nanotube interaction energy. But what happens if the nanotube is infinitely long and if your graphene nanoribbon is limited? Then what will happen if you put in a very low temperature and very slowly? It will not roll at all. Okay, it will just sit there as simple like a rope. Because think about it, it will still enjoy the same graphene nanoribbon or graphene nanotube energy. The energy amount is same, but in this case, it has to pay the rolling energy, the bending energy. That is squeeze, it has to bend it. But if the nanoribbon is infinitely long, it can just sit inside. It will still enjoy the same amount of energy. Okay, so depends on the system, you can generate different kind of nanostructure. Okay. It also depends on the temperature. Okay, so if you put a different chirality of the nanotube, you can have a different chiral structure. That means the pitch, you can control the pitch of the helix based on the chirality. But if you increase the temperature, what will happen? The extra energy that will enjoy because of the chirality, sometimes called Piper stacking energy, it is very small compared to the kinetics. Okay, compared to this kinetic energy. So if you have a very high temperature, you have a different structure. If you have a low energy, if you have a low temperature, you have a different structure. If you have a limited length of the nanotube, you have a different structure. If you have a very long nanotube, you have a different structure. So that's the whole picture. So you can control, or you can generate different kind of nanostructure based on what you have or how you can control it. That's the idea. Okay. So that part the material is gone. So now we are going towards mostly biosystem. Okay, so here this is a collaborative. Actually, initially it was a collaborative project. Okay, so that's the last two paper we actually published in a very good journals. Probably the undergraduate student do not have enough idea about the journals. So the first one was published in Nanoletters, and the second one was published on ACS Nano. Those are very good journals in chemistry research field. This one is little different, and this one is very complex. Okay, so here the idea was can we generate a kinetically stable micelles? Probably if you are in BSc, you know what is how the micelle is formed. Okay, so that the thermodynamics of the micelles. Okay, so if you know the thermodynamics of micelles, and if you do not know, you can ask me later after the talk. Okay, so if you have some drug molecule, and if you wanted to put the drug inside the micelle, or sometimes we call in the core of the micelles, at equilibrium, the number of drug inside the micelle will be almost fixed. Okay, almost there will be a Gaussian curve, but you cannot have a huge number of drug molecules inside the micelles. And also, the micelle size would be constant given on some particular conditions. Okay, so this is the thermodynamic polymorphism. But the problem is, if you want to deliver a drug inside our body, you need to have a micelle which is sufficiently stable. That means you do not need to be. You do not need to be thermodynamically stable. If the kinetical stable micelle, or if the lifetime is good enough, but the important part is if the drug load is maximum. So what the purpose is, can we have a micelle which is sufficiently stable? And the most important part is, can we have more and more drug load compared to the thermodynamic equilibrated micelles? Okay, so that's the goal. The goal is to increase the drug load. Okay, and the drug load is defined by the number of drug molecules inside the micelles in a simple language. Also, this is not exactly correct because you have to define some other parameters. But so let's stick to it in a very simple language. You want to maximize the number of drug inside the micelle. So if you want to deliver a drug inside your body, you need little number of micelles. That's the idea. Okay. So if you want to generate a micelle, you need a molecule, okay, which has a different volume ratio from head to tail. If you have the both volume ratios same, the head to tail, then you may not get a micelle. You get some kind of bicell or sometimes tubular structure. Okay, so that's why you choose a lipid molecule which is biocompatible. Okay, so we did a simulation, but this simulation is different. The first simulation was like a, sometimes we call all atomistic simulation. That means we consider all the atoms explicit. Here, this is called the coarse grain micelles because the system is too big. We do not have enough computer or the resources so that we can count. We can take every atom individually. Okay, so these are the system size are like almost like more than millions. Okay, so what you do actually not more than millions. Beats are more than millions. In a real sense, it could be 20 millions or so. Okay, it could be 20 millions, and you can think about it. In order to simulate a 20 million atom, we do not have computer in India right now. Okay, even if we have in here, it will not get results. 20 million atoms, we do not have computer in IIT, at least in our IT. Okay, so what we do actually, we use some method, sometimes called coarse grain method. And in a nutshell, I'm going to tell you what is coarse grain method, where you basically took certain number of atoms and put it a bit. Okay? Sometimes 4 carbon, 5 carbon, 6 carbon, and you represent as a single bit. It behaves like a single atom. Okay? So we reduce the size of the system. Okay, so that's technical part. This is not so important for the undergraduate student. So what you do here, we choose a lipid which is biocompatible. Okay, you can see this is a kind of drug molecule. You can consider it. Okay, this is just a hydrophobic molecule. We just replace this is a hydrophobic molecule as a drug. Okay, and this is a lipid structure. You can see this is a double-headed lipid, and this is a tail. So the volume ratio is good enough to make a micelle. So we take a nanotube. Okay, we put the red molecules, which is basically as a replacement of the drug, and then we put a lot of these lipid molecules in the water box. Because this volume structure is different, after a certain time, it will form a pre-micelles. What is pre-micelles? You can see that on a you can see there they can already make a curvature. Okay, so because this kind of volume ratio, the head is kind of higher volume compared to the tail, they already form P micelles. And then what you do is we basically apply a force from the left hand side to the right hand side, and different forces on the molecule, the red molecule, which are the kind of mimicking of the drug molecules, and the water is nothing but you just vibrate the waters. Okay, and you can see that eventually in the water you have a different micelles, and the red molecules are quite high. And we compare with the same system with the when it is without the nanotube. That means in a thermodynamic system, and we see there is a more than 10-fold increase of the drug launch. And also here you can control the size of the micelle by choosing different diameter of the nanotube. That is important. So you can control the diameter, or you can control the size of the nanotube, and you can also control the drug payload by choosing a suitable speed or choosing a suitable pressure of the drug molecules which are inside the nanotube. Okay, sometimes this is we call the micelle producing machines. Okay, but this is a fancy name. What happens if we have a lipid molecule? This is just a comparison purpose. Okay, so if we have a same volume, okay, then you might not get micelles. You get some kind of tubular structures. So this is not micelles. Okay, so let me show you a movie. Taken back. Look at the first structure. It's already formed P micelles. Okay, and eventually it will form micelles. Okay, you see the micelles. Actually, now you can question me why the second micelles are smaller and smaller, because we do not have enough molecule and the force is constant. Okay, so in principle, in a nanotechnology, if you have continuous source of the lipids, okay, you can even produce a similar size of micelles. Of course, you cannot have the same size every time, but the distribution should be very narrow. Okay, and you can see the second one. The second one is basically single head and single tail. You cannot have the micelles. You have basically a bicell structure, which is actually not very useful in drug delivery purpose. Okay, so that's the idea, that you can control the micelle size by choosing a different nanotube diameter. You can control the drug load by choosing a different speed by which you can basically push the drug from the left hand side. Okay, so here what we achieved actually, that we can generate or we can produce a kinetically stable micelles which has very high payload or drug payload. Okay, which can be used for drug value system. And we published this paper in JAX, and probably undergraduate students may know that JAX is one of the best paper in our field. Okay. So this is a collaboration with a pharmacy guy. Okay, the pharmacy guy, and his name is Sing Pyo Hong. He is now in Wisconsin Medicines. The goal is almost similar, but it is different. Okay, I mean it is little different. The structure is little different. Probably you know what is dendrite if you know the organic chemistry or some polymer chemistry. So so this part, let me show you. So this part is the dendron part, okay, the solid part. So basically it is used to increase the chain, okay, it's like a finger. And you have a lot of functional basically points here. So you can functionalize this part, okay. And this blue, this hairy part is basically nothing but the peg, okay, the peg. And the tail part, the red part, is the PCL, polycaprolactam. So this is a monomer. But the important part is in order to increase the head size or the head volume, you use the dendrite, okay, you use the dendron, okay, and the dendron has a different generation. This is actually third generation dendron, okay, it's kind of a branch, it's a lot of branch. So you increase the head volume so that the CMC or the CMC is extremely low. Okay, you know that CMC, right, critical micelle concentrations. So you need a minimum number or very small number of monomer in order to form a micelle. Okay, think about a spherical ball. If the volume of the tail is compared to the head is very low, then you need minimum number of or very little number of monomer in order to form a spherical ball, okay, or sometimes called micelle. So that's the goal. That means that it should be a low CMC solution, so low CMC polymer. Okay, so they did a lot of experiment, but they could not understand what are the best molecular compositions so used for the can be used for the drug delivery system. So we simulated different systems. So right now we are showing only the 4. The first part, there is no dendron. Okay. The second part also there is no dendron, but the difference is with the red part. Okay, this is a 16 kilocalorie, 16 kilodalton peg. So that means the peg chain is huge, but this is only one peg chain. Okay. The third one, the yellow part is the dendron part. Okay, and the peg size is same for all the peg, like a 2K. Okay, and this guy, the extreme, the fourth one, the D1, the PCL is quite big, 14K. So there are different composition, different structures of the monomer. Okay, the first one 3.5K PCL, but the peg is 2K. The second one is again the core is same, the 3.5K, but the peg is very long. And the third one, you have 3.5 PCL and 2 M. Okay, this M is the number of peg. It depends on how many branches you have. Okay, and this G3 means is the generation 3, third generation. Right now they have 5th generation actually available in market. Okay, and the fourth one, which has a very long tail, 14K. Okay, but again this is a G3 and the peg. Then we simulated all of them and we figured it out, the micelle, which are basically like this. Okay, the micelles, and we see that B is the most suitable candidate. B is the most suitable candidate. Okay, for the drug delivery system. Why? Let's discuss about the first. What is the problem with the first micelles? You see the blue part. The blue part is basically a hydrophobic part. So if you inject a micelle with the drug, or with this kind of micelle, what will happen? This hydrophobic part and the other hydrophobic part of the micelle, they will interact each other and then coagulate. It will not basically travel to the blood. This is not good at all. The third one, this is also not so good because you increase the size of the size so that now the yellow part is also now visible, because now you do not have enough also. This is also not good. But now see the B part, you do not see the blue part at all. The blue part is basically bad for the delivery system because the water, that blood also like the hydrophilic part, and that's why you choose the peg. Okay? By the way, these structures are FDA approved. Okay, so if you do not know FDA, the undergraduate students, so they basically control. Okay, so this is a loose sentence, but almost you can think about they are the big control regulatory body Hello? 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 Uh-oh, there is something wrong. আমি যখন এন্ট্রি করেছি আর 10-15 মিনিট ধর, যতক্ষণ বলি ততক্ষণ কন্টিনিউ করতে পারো, কোনো অসুবিধা নেই। হুম 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 আমি তো ঢুকতে পারছি না, হ্যাঁ কিছু একটা প্রবলেম হচ্ছে আমার মনে হয়। চাচা আমাকে ঢুকতে দে। আমার স্লাইড দেখতে পাচ্ছিস? I just don't understand. There is something issues. There is some internet issues, I guess. Okay. Am I audible? I think there is some power problem or shutdown. Hello? Hello? Can I continue? Can I continue? Okay, thank you. Do you see my slides? The slides were already shared, no? The slides are already shared. Okay, thank you. So let me know if you have a problem, you just call me. Okay, so what we did after that, we try to understand with this kind of stuff. Okay, so I think we have 10-15 minutes left. So I'll continue with various very deep. Okay, so this one is the project that we did it. I think undergraduate student might be interested about this. So this is an enzyme called catechol methyl transferase. Okay, this is an enzyme called catechol methyl transferase, and this is largely responsible for Parkinson's disease. Okay, so what it does, it basically deactivated some of the neurotransmitters, sometimes called catechol. Okay, and in our undergraduate chemistry, probably you know already dopamine. Okay, molecule called dopamine. And the dopamine is actually one of the neurotransmitter that's used for the Parkinson's disease. Okay, I'm not audible. What is going on? Hello? So what you want to do here? How we can design an inhibitor so that we can stop some of the mechanism by which the neurotransmitter was disabled. Okay. So this is an active site of the enzyme. Those who know, probably the undergraduate student do not have enough exposure of the biosystem. So this is a protein called enzyme. Okay, and the name of the protein is called catechol methyl transferase. So in the active site, there is a magnesium, and there are some other substrate called SAM and some other protein residues. Sometimes these are the name of the protein residue. So there is an octahedral environment. So when the neurotransmitter comes very close to the active site, it basically transfer one of the CH3 group to the neurotransmitter. Okay, so basically it's like a methylation. You can call the methylation. Once the methyl group is attached to the neurotransmitter, that neurotransmitter is useless. Okay, so then the brain do not have enough neurotransmitter to do all this signaling process. Then we have this Parkinson's disease. This is simply as that. And as a remedy, actually, we all supply. Actually, they supply this L-dopamine. Okay, and actually, you know probably that because of this L-dopamine, I think there are 3 scientists, if I remember correctly, from the Sweden. Some Dr. Carlson and Kendall and Greenwald, and they got Nobel for this L-dopamine. Okay, so our goal was to develop some inhibitor so that we can process or we can stop the process of this methylations. Okay, so we did a lot of studies. What are the mechanism by which they produce all this methyl transformation and everything, and eventually we in this paper we understand the mechanism by which they transfer, by which the substrate basically transfer the methyl group to the neurotransmitter. Okay, so we understand that after some point in the simulations, the basically the octaedral environment completely flipped. Okay, so the neurotransmitter changed its positions. Okay, if I see here, you can see that this is a particular octaedral environment. See, you see, this is a octaedral environment. So this is see the methyl will transfer here. Okay, the methyl will transfer here, and this is the hydrogen, and these are the O and O. This is O minus. So the O minus, the CH3, and this is a sulfur. The CH3 group will transfer to the O minus, and then this molecule will left from this octaedral environment. And another neurotransmitter will come here, and another CH3 will be here. It is like a continuous process, and the concentration of the neurotransmitter in the brain will decrease. So brain will not perform perfectly. Okay, but during the mechanism study, we see that actually this guy is not stable. Okay, so this guy is not stable. So can we have a stable molecule mimicking the neurotransmitter, which is extremely stable? If we block this octaedral environment for a very long time by doing some stability, okay, by some addition of some molecular formula or addition some functional group, then what will happen that the octaedral environment or octaedral active site is not free. If this octaedral environment is not free, then there is no questions of deactivating of the neurotransmitter. Then your brain will work. Then your brain have enough neurotransmitter, and it will work as a fine. And this is exactly this L-dopamine does. Okay, so with L-dopamine, which is a neurotransmitter, and in the real medicine, they actually also add some inhibitors. Okay, so the inhibitor actually blocks the particular active site, and L-dopamine, which is the neurotransmitter, it just works fine. Okay, so that's the goal. So we did the complete study and we try to understand. So basically there is a flip. So if we can stop the flipping by some similar kind of molecule, which is not a neurotransmitter, but it should be very similar, otherwise it will not fit there. Okay, so we design a lot of molecules. We try to understand what are the mechanism by which. So these are the activation energy. Okay, I'll take only 10 minutes. Okay, so these are the different. Okay, so now this is a chemical reaction. So we use a different method, sometimes called QMMM, quantum mechanics, molecular mechanics. So this is a hybrid method where the active site is designed, the force or sometimes the energy is calculated by the Schrodinger equations. Okay, and the rest of the protein is just a classical simulation. So this is basically it's a hybrid method. This is sometimes called QMM studies. Okay. So these we calculated different contribution of the different residues, and right now we are preparing one paper using sometimes probably undergraduate students are not so familiar with the term machine learning. So we design a library of almost 20,000 molecules using a software. Then out of it, we selected 10 molecules which can be best candidate for the inhibitor by sometimes called machine learning methods. Okay, so we're going to submit the paper next week, hopefully. My students are here. Unfortunately, we do not have enough students here, so they are working from home. Okay, so the last part that we want to talk about here, that part we are working here, and this is sometimes called efflux mechanism. And most of you know that the drug resistance problem. Okay, so if you use a drug for a very long time, then somehow your cell has a memory that this is a foreign body, and then the cell does not like it. It will immediately expel the drug from the cell. If the drug concentration in your cell is not good enough or not sufficient enough, it will not work. So there is a particular protein called the efflux pump by which the drug is expelled from the cell to the outer cell. Okay, and it looks like this. Okay, so this is a membrane. Actually, this is a part of the membrane. This is cytoplasm. So this is one of the. We are working on it. This is a MEXB. The name of that efflux pump is called MEXB. Okay, so these are the different parts. So this is the inner membrane part, and this is the outer membrane part. So the dust comes from the low side, which is basically the cell, and then there are some mechanism we might discuss or might not discuss here. It will just go outside. Okay, so again, our goal is first is to understand what are the mechanism for this particular efflux pump, so by which it basically expels the drug. And once you understand the mechanism, can we design an inhibitor so that we can stop the mechanism, so that even the drugs are here, even the cell identifies that the drugs are foreign body, it cannot expel. So if the drug is inside the cell for sufficiently long time, because it does not have path to go outside, then it will work as it's supposed to be. Okay. So this is a real structure from the PDB. Okay, this is a real structure of this lower part. Okay, so what I show here, only the blue part. Okay, so this is the blue part. This is the blue part, and the blue part is basically trimer. The similar protein is a trimer, and it has a three pockets by which the drug basically enters, and it's changed. There is a rotational mechanism we might discuss. Okay, here it is. So at a time, it can have tight, loose, and open mechanism. It basically rotates. It's called rotation mechanism. It's basically lock and key. So at a time, it rotates, something like this. It's basically as it forms tight to loose to open conformation, the drug will basically travel from the lower end to the upper end. Okay, so the goal is to stop that rotation. So you have to design a molecule in such a way that it would slip to a particular place of the protein and it stop the rotations. If you can stop the rotation, then the whole process of the drug expansion can be stopped. So in order to do that, first you have to understand the mechanism. Okay, so these are the three molecules are available commercial. Okay, so these are the first generation inhibitors, these are the second generation, and this is the third generation. And by far, this is the most commercial success efflux pump, irrespective of the efflux pumps of this R&D. This is also good for another pump. Okay, ACRB. And then we see that why it is good for this. So we understand what are the mechanism or what are the residue that is interacting with all this. I'm going to show you here. Okay, again, so this is an active site. Sometimes we call distal pocket. Okay, so it has a pocket. The protein has a different pockets and in a different positions so that it can bind there. Okay, so we try to understand what are the responsible residue by which it interacts with the molecule. Okay. So this is the different configurations, A configuration, B configurations. So at a different configuration, the protein has a different residues which are exposed towards the molecule. So what we want to do is here, by understanding which residues are important, towards the interactions, can you mutate some of the residues which are not interacting right now? But if you mutate it, it might interact with more. If the interaction is more, then what will happen? You can stop the rotations. So that's the goal. So you want to increase the binding energy with the ligand or the inhibitor or with the protein, so that the binding energy, so that the inhibitor will stick to that pocket. If the guys stick to the pocket, the whole process will stop. Okay, so that's the goal. So we did again all this rotational or all these studies, and these are the contributions, different contributions. Okay, sometimes you need to understand different contributions. Okay, electrostatic, van der Waals, and everything. So part by part. So these are the compositions of the interactions energy. Okay, so I'm not going to talk about all this. Again, we did not only the classical, we also introduced this KMMM study with this big protein system. Okay, then we see that there is a significant difference between the structure when you do in the classical level and the quantum level. So we might need to consider some of the quantum structural effect in order to design the inhibitors. Okay, because quantum will supposed to give you the better results compared to the classical. Okay, so we published this paper in Campus Cam, and also this is a cover features. And I would like to stop here right now. And these are my students, and these are two MSc students, and these are PhD students, and this is our institute. This is the Heritage Building. Actually, it was Indian School of Mines. In 2016, it converted to IIT ISM. Okay, thank you. So if you have any questions, I would be happy to answer. So first question, what is the most active structure of graphene? I mean, with what respect to what? Active in a sense. In this case, this is a classical. Do you hear me, right? Hello? Can somebody talk to me? Hello? Okay, so The question is little. The question is not complete. I do not understand. What is the most active structure of graphene? I mean, active respect to what? So, are you talking about the electronically or in with respect to our simulations? In our simulation, the graphene is not actually in the first part. It's not chiral, and it is not even if you see that even if it is not terminated by hydrogen. So this is just a demonstration by which you can control the nanostructures. Okay. But this active structure means it depends case to case. Okay, it depends case to case. So you cannot say this graphene structure is active or it's not active. Is there any other questions? Okay, so how the biocompatibility is kept in mind. Okay, so that's important. So this is so you have to check first the polymer. Okay, so so the biocompatibility. Okay, so I guess you're talking about the polymer biocompatibility by which the micelles are formed. Okay, typically you should keep in mind that all the molecules that you are going to form the polymer, okay, these are block copolymer, sometimes linear copolymer, dendrite polymer, they should be clipped. Clipped in a sense, if you have a big molecule, you inject in the body, and you should have enough enzyme inside the body, mostly some kinase and some other transferase. They should chop the molecule. Okay, so that's why you use the PCL. There are some ester bonds, there are some other bonds. They should chop the bond, and the molecule is such that they should pass through your urine. It should not stay there. They should not stay there. Okay, and this is one of the criteria that you should track the molecules. Okay, so actually they do by tracking with adding some fluorophore. Okay, some probably some who does the bioimaging. Okay, they wanted to track over the time where are the molecules. Okay, so that's the biocompatibility. It should not go to your blood barrier. It should not cross like it to your brain or everywhere. It should not do any bad part. Mostly, the goal is the big molecule should not stay here, and in order to chop it, you need to have any chemical bond which can be chopped or which can be clipped by the enzyme which are already present in our body. Okay, so that's the meaning of the biocompatibility. It should not have any adverse reaction. It should not stay in the kidney. It should not actually go to any other places. Okay, so for example, this the painkiller paracetamol is still okay, but if you take any ibuprofen, they are very bad. Okay, they can stick to your all the path, and they can go inside your body. That's why they said that don't take painkiller for a long time. The concentration of the painkiller, the NICE is very high, then they can go to anywhere, and they can stay in the kidney. And if you take all these bad molecules for 1 month or 2 months in a high dose, there is a possibility that kidney can go bad. Okay, but mostly you need to make sure how much you are taking and how much you are passing through the urine. Okay, this bag all molecules actually the body does not like anything which is not actually close to this protein type or lipid type. Okay, it doesn't like it at all. So that's why actually the body has different mechanism or different enzyme. They basically chop all this organelle. Actually, the COVID, right? So they, the remdesivir structure. If you know the remdesivir structure, they did a particular change in the bond. Okay, so initially the original structure, I don't think this is a discussion about this remdesivir or COVID structure, but if you see the remdesivir structure, they change the CC bond so that the enzyme which is present in our body cannot chop it, so that it can be there as a prodrug. It's a beautiful thing. You see the history of the COVID, the remdesivir design, and you'll be amazed at how the scientists have identified which enzyme can chop it and what are supposed to do in order to not to chop it. Okay, is there any other questions? Can every neurotransmitter show that? No. Neurotransmitter is a general word for different class of molecules. This is what I'm talking about. This is only related to the catecholate. You might have different enzyme for different neurotransmitter. Okay, so this is only for the catecholate type where you transfer the method. Okay, so there are different class of neurotransmitter. This is one of the class. Okay, so this CMT is actually well studied and this is well known. Okay, so that's why we do it. There are so many enzymes in our body, in the brain. You can have different enzymes, different class of neurotransmitter. Every neurotransmitter has a different role, and this is one of the class. The catecholate has a different class. Any other questions? Okay, so if not the questions, I think I would like to thank you again for all of you, especially models. So can you talk to only the SAR, or maybe, okay, is there any substitute of graphene? Yes. So after our paper, so what do you mean substitute of graphene with respect to our study, or graphene with respect to some other properties or other thing? The question again is not complete. Substitute of graphene with respect to as an electronic device or something else for our nanostructure. And why do you want to substitute? Where? With respect to? Hello? Okay, so look, let me put it in a different way. Okay, so if you're talking about our system, that what we simulate here, of course, you can take any other polymer. Okay, you can take any other polymer as long as the competition is well. Okay, so the competition, you see, the bending energy has to overcome by the water and the polymer at the very beginning. Okay, but at the later stage, it has no role. The polymer can go by itself as long as this is hydrophobic, and hydrophilic. But what you are talking about, is there any substitute of graphene? Okay, the graphene, if you're talking about electronic device, actually initially in the 2000 or so, in the beginning of the century, everybody was excited about graphene can be used for the electronic devices. But so far, it has not shown so great. Okay, it could not be materialized. Okay, so they do a lot of stuff. They modified a lot of with the different they modified these graphenes with different you cannot even imagine. Okay, but it has not shown so promising as they thought. Okay, still the silicons are the best bet. Okay, but now actually Sarah was telling that now actually they develop a different material. Now the materials, okay, graphene has an advantage that is very thin, but mostly the electronics world might go to the very composite materials. Okay, so not maybe the silicon in a different way. Okay, so with respect to walls, you can take any polymer as long as as I discussed, the energy compositions are well in the very beginning. It has the water and the polymer energy has to be high, and the later it does not matter. Hello, so you done? Camera is on. Oh, my camera is on. Oh, you're talking about probably Asad. You're talking to Asad. So just for the undergraduate student, if they're still here, I just to suggest you the history of the remdesivir molecule. Although it is not actually developed for the COVID, it was actually developed for Ebola. Okay, but you just see the synthetic history. Although I'm not a synthetic guy, I'm just a pure computational guy. But read the history how they developed this drug. You know, at least you read one of the history of the drug development. See, chemistry is amazing.
Okay, since there are no more questions, let's conclude the session. Thank you very much, Dr. Patra, for the very nice and illuminating lecture presentation. I think now we have a lunch break. So it's, we'll not be able to serve you lunch, of course. Huh?
So I might not able to join the second half because I have a class from 2 to 5. It's a practical.
Okay. Okay, that's okay. That's fine. Okay. So I think we will come back at 2 p.m. After the lunch break.
Right. So can I leave now?
Yeah, sure. Okay. Thank you very much once again.
Thank you very much.
So we shall all leave now. We will come back at 2 p.m. I think the YouTube link will be same, I think. Or it will be different. The link of the YouTube link. So there's another link. I think it has been sent to you. It has already been sent to you. So so you have to follow that link to join the next next session. So till then, I think we shall leave now then. Goodbye till then. We will join back. Yes, we are ending the broadcast now.